My name's Doug Murray. That was a pretty good introduction to me, I guess. But I did grow up here in Juneau, went to school in Fairbanks. I know actually lots of you guys. Some I even went to school with. And pretty active in the community, and youth athletics and that kind of thing. My talk today is on geothermal. I heard advertised it was about the aquatic center geothermal system, and that was kind of a surprise to me this morning. So we hastily put in a few more slides on the aquatic center. But generally, this is a general discussion on geothermal. Let's see if I can get this to work right. So why geothermal heat pumps? Well, just a little bit of background. Oil-fired systems and even propane systems are somewhere in the range of 80 to 85% efficient. So what does that mean? That means for every dollar of fuel that you put into these types of systems, you get essentially 80% of your energy out of it, right? Everybody's kind of used to that figure for oil-fired, I would think. Electric boilers, 95 to 100%. Some people claim 100%, but when you look at the whole system, there is a little bit of a loss there. Heat pumps are not normally thought of in terms of efficiency, but they would range anywhere from 250 to 400% efficient. So right there you can see that why there's interest in geothermal for heating and cooling applications. I'm not going to read all that stuff. You guys can kind of follow along with me. There's just some reasons there why geothermal maybe should be considered. This up here is a typical geothermal vertical bore system, and this is actually patterned after the airport, as you'll see here in just a second, where we have a loop field in the ground. We have some circulation pumps that moves the fluid from the ground up to water source heat pumps that then move that energy out into heating and cooling. So one of the aspects of heat pump that I'm sure I'm going to get is how do they work? And we'll get into that a little bit, but one of the things I want to keep saying to you is that a heat pump system doesn't make heat, it moves heat. Okay? And that's really important to think about. That moves the heat. It's not making it. So essentially we're moving heat in the geothermal aspect from the ground, and then through a refrigeration process, then we translate that heat into the building, heating or cooling. So one of the first projects that came about, other than the AEL&P project that was done about 17 years ago now, was the airport. And essentially early on, the project manager came to me and just said, is it possible to do this? I'm like, well, sure, it's possible. And she said, would we be interested in participating in a analysis of it? And I said, sure. So we went in with Alaska Energy Engineering. It's another local engineer, and went through a life cycle study on it, and determined that it had merit. But boy, is it expensive to put in. And so if you can get past, essentially, the initial cost, then things start to look pretty good. And so here you can see what that initial study and cost ended up being, and that was not only our cost, but it was also the airport administration costs. Just an example of the system here, a little bit more in depth. The airport system consisted of 108 vertical boreholes that are located out in front of the wings airways. We got approximately 16 miles of plastic pipe, and that is delivering heat to an ice melt system out in front, which is the sidewalk, and then the raised area across to the bus and taxi waiting area. That's all heated from the ground, and we do that with there's about 32 heat pumps in the building now. 3 of them are water to water, and those are the ones that supply the heated water for the snow melt system out in front. And then we have actually one dedicated outdoor air system that supplies outside air to all of the heat pumps that are throughout the building. So I don't know if folks noticed last year, but last year at the airport was really the first year that the sidewalk system was in use for the whole year. And I didn't see anybody shoveling out there. So, and very few chemicals, if any. So it seems to be working pretty good in that sense. Here was the conceptual design, and so here you can see the loop field. That's the 108 boreholes there, out in front of wings. And this is just a conceptual for the entire airport for heat pumps everywhere. The heat pumps actually stopped about right here, and this is really the only spot that they are on both floors. The old portion of the airport didn't undergo any of the renovation, at least in this phase. They're hoping within 5 to 10 years that they can do something to that area. And when they do, this loop field should just about be sized for a pretty significant expansion of the airport. So here's where they got started. So this is out in front of wings. Gregory Drilling from Washington was the successful bidder on the vertical boreholes. Harry's Plumbing and Heating did the horizontal plastic pipe. But these guys had to come in and do the drilling first. And you can imagine at the airport, it was quite the ordeal with, they pretty much had to cordon off the whole area and be careful. Everybody had to be badged, all that kind of stuff. So it was quite the ordeal. Here's joining some of the plastic pipe. Here I am. I'm observing a plumber with Harry's there. He's applying some of the fusion to the pipe itself, and this is how they pretty much join the joints together. It's a heated process where you can pretty much see once they melt the pipe together, there's no joint really. In fact, the joint is actually stronger than the pipe. So I tell you, in the last 10 years, HDPE has been kind of an unsung revelation because there's a lot of uses for HDPE pipe that weren't around 10, 12 years ago even. So it's a really good product for this. Anyway, and so here you can see some of the tails coming off that would feed the individual loopholes. And here we got the mains. And I got better pictures to show that, but just to kind of give you an idea. So here's back to the airport, and you can see that we've got the mains here, and these are the loopholes that will go out and connect to the vertical boreholes. So the plumbing contractor has brought all the stuff to the site for final assembly. Here you've got a vertical borehole that goes down. It goes down about 350 feet, and it comes back up again in a U-tube fashion, and then connects back in with the main. And here they're just starting to put the mains in, and this is more of a completed deal here. Where you see here's the boreholes, and these were at 15 feet on center, and they're joined together then in a main that is then brought around to the building. And here you can see we've got the 4 sets of sections, 4 different loop fields. They're all brought into the building, and then we manifold them there and bring them into the building. This here was the completed, when they finally got the tarmac back onto the spot. So you don't see anything out there. This is the outside. We had to build a little shed. As you saw these pipes coming up here, they built a shed around this. That's what this is here. And here's one of the plumbers. He's working with the piping that's then is going into the pump room. And then here's your main pumps that are in this room that then circulate the fluid throughout the building and then back down into the vertical borehole loop field. Inside the building, here's what some of the piping looks like. I realize it's kind of boring, but it is exciting to me. Here's a water to air furnace. And it's a little bit bigger than, say, your residential type furnace. And this is on the floor. And then here is one that's actually up in the ceiling. So, at the airport, we've got about 32 of these things. Most of them are above ceilings. And that was done mainly because real estate is so precious at the airport. The ice melt system. Here we have 2 of the 3 water-to-water heat pumps. And these things take the geothermal fluid in and through the refrigeration cycle, squeeze the heat out, and then actually store it in a big storage tank that's over here. And then the radiant heating system siphons out of that big storage tank, and it goes down into the radiant tubing, as you're seeing right in here. Here's one of the pits that's out right here, actually, with the manifolds in the pit there. And this is the radiant tubing that then goes out into the sidewalk. And the heated fluid is actually in this copper pipe that came over in a main to it. So you can see quite a bit of it. This is already paved here, but this has got the tubing underneath it. And then over here, where the taxi and bus waiting area is, that's also got a snow melt system on it also. This is another picture of it. A lot of tubing. And as with most modern buildings, the airport was upgraded with DDC type controls. These are some screenshots of the graphics on the computer system. This one here is kind of handy. You can barely see the green and maybe a yellow or two, but these are indicators across the floor plan if zones are hot, cool, or cold, you know, that kind of thing. So it's real nice for the maintenance folks to have something like this, you know, with just one, you know, one or two graphics, you know, they can get a pretty good idea of how their building sits. Geothermal is part of a building system, you know, not only with the heating system. You know, what we really need is, you know, high performance envelopes, you know, energy conservation, that kind of thing, in order to keep our utility bills low. And that was the big goal of doing this at the airport, was to really keep operating costs down low. The project received a 2010 award from the Alaska Community, the Alaska Municipal League. Geothermal design challenges. So, collaboration between owner and designer is a big one. You know, I'm quickly becoming the expert on geothermal. I do not consider myself an expert. I'm just one of the engineers that has tried to dabble in this and figure it out. Typically, geothermal is used for cooling applications down south. The heating side of applications is increasing, but to be honest with you, about 80% of the applications out there are for cooling. And so when we talk to manufacturers and the like, you know, we have to keep in mind that they're probably talking from a cooling aspect and not a heating aspect. And that has come up as some of the problems that we've experienced, say, at the pool and a little bit at the airport. And I'll get into that maybe a little bit. Who's responsible for the design? You know, it is a specialty expertise, although I think at this point the Department of Labor has determined that the mechanical code actually governs on this. Lack of product expertise, that's kind of what I was referring to in terms of cooling applications. The sales reps and such don't often understand that we're using this for heating, don't often understand that our ground temperature, you know, is an average of, say, 42 degrees, which is pretty low to try to get heating out of. So there's a lot of those kind of challenges that we have to work through with the actual product. Breaking the work into two components, that was decided to do for the airport, mainly because they saw the drilling as a pretty huge cost. And so that was done on that project. In several of the projects that I'm going to show you at the end, that is not the case. So, yeah. Test boring challenges. I got some more slides a little bit further on, but obviously there are some challenges with the terrain we're in. At the airport and the pool, we discovered basically that it's moraine material, all gravelly type material, 350 feet down. And that turned out to be a problem, you know, when they're drilling a 6-inch well all the way down and they pull out their drill bit, and now they're going to shove, and that's what you see right there, is they're starting to shove this double tube down into this hole, 350 feet of plastic pipe. First 250 feet usually goes pretty easy, and the last 150 feet is very hard to push down in there. And there's really no other way to do that. It's plastic pipe, so you can't put something heavy on it. It's pretty much got to be manpower. So that's difficult. And what they discovered at the airport is that the holes would start collapsing on them. You know, if they didn't do this in a hurry, like they couldn't drill a hole, pull the drill bit out, you know, and because at 6 o'clock leave and then come back the next morning and try to, you know, push the tubes in, wasn't going to work. Another problem that they discovered at the pool was the first 30 to 40 feet that they drilled through was a stump dump. Some of you remember that, Red Sam, they had a pit there, and a lot of stumps and cars and stuff, got down the ground, and so what would happen is those wood products were real soft, and so they would immediately collapse in on the hole. So some of those holes they actually drilled 2 and 3 times. So what they ended up doing there is just putting casing down in, the first 40 feet, and that helped hold the hole up until they could get through, the organic material. What I've discovered recently on a couple of other sites, and I'll get into that a little bit, is if you can get away from the river valleys, you're actually into bedrock, which is a much more conducive material for us to transfer heat in, as I'll explain a little bit later. So bedrock takes a little bit longer to drill in. It's the same equipment. It's a wet rotary drill. So it's really the same equipment, just takes a little bit longer. Contracting challenges. The way we always do it, thinking, well, obviously that's going to be pretty tough with geothermal because we don't have a way we always do it, unless you talk to the drillers down south. You saw a picture there of Gregory drilling, and I have an analogy for him. I forget what the name of the movie is with John Wayne when they went and they would put out fires on the Texas oil wells. Yeah. Anyway, but I think a lot of people have seen that movie and you get the idea of what the people were like. Well, these guys were just like that. It's like stay out of their way. Stay out of their way. If they saw somebody from the city coming, they were immediately looking for me to get in between them. Because they just wanted to do their work. They had a groundbreaking ceremony at the pool. And we basically had to threaten them to shut the drill down so that everybody could do their shovels, because they didn't want anything to do with that. They just want to do their work. Well, that mentality is really kind of part of the whole drilling mentality. They know best. Get out of their way. They'll do it. So that's part of the challenge of the way we always do it. Another one really is IGSPA certification, which is the International Ground Source Heat Pump Association. Before I really got into this heavily at the airport, I went down with another colleague of mine and we got IGSPA certified, and that was real enlightening in that I was in the middle of the room with probably 75% contractors maybe and maybe 10% engineers. But it was really enlightening to listen to them and to hear what they've already been through. And IGSPA is real adamant that a lot of things need to be IGSPA certified or contractors need to be. I got a lot of pushback from that in the state of Alaska because there's very few people that are IGSPA certified, and so that was tending to point work down south. That's changing. I think here in Juneau there's probably 5 or 6 people that are now IGSPA certified. 2 in our office, but. Some of the challenges. This is the airport again. Weather too hot. Gee. In Juneau? Yeah, it really was. So this is out in front of Wings, and if you remember 2 summers ago, we had just an awesome summer there, and it got too hot for them to fuse the pipe together. It was reading about 115, 120 degrees out the bottom of that pit, and what the challenge there was is that it would take much longer for a particular joint to cool down so that they can even move it. So labor increased because of the temperature. Too wet. That same summer, just about a week or 2 later, this is what happened. And they basically had to stop work for a couple of days. So there's those challenges also. Geothermal well testing. This is one of the things that you'd like to think about for each project. Maybe as we get more experience, we don't have to do as much of this, but what we're doing here is we're essentially testing for the thermal conductivity of a well. And as I indicated, you have gravelly soil in the valleys. That's, to be honest with you, is a very poor thermal conductivity. Where we have bedrock in areas like at Auk Bay, that's a very good thermal conductivity. The range went from, in bedrock, thermal conductivity is about twice as good as what's below the airport and the pool. just give you a nice range. Is it important to do that? Yes, it definitely is. I mean, you need some idea of what your geothermal field is all about, you know, what's down there. At Auk Bay, we just got done 2 weeks ago doing one well, and we tested it there, and that is essentially 95% bedrock, which was great. It's just really good news. This here is the test kit, and I've essentially leased this for a while to use because I've got about 4 different sites that we're testing this year. It's about 3 by 3 by 3. It's a very simple device. It's just got a heater and a pump down in here, and then a little computer unit here, and you hook it up for about 2 days, 2 to 3 days, and you send heated fluid down a well that's already been drilled, and then you send the data back to the lab, and they'll analyze it for you for thermal conductivity. That's the kit as it was set up. This is a really poor picture, sorry. The tires are being used as a stand so that we can get the thing above the borehole, which is over there on your left, so we don't trap air. The white thing is just a big blanket that they supply to try to keep the heat of the box inside, or try to keep your heat loss minimum. So that's essentially the test as it's set up. This was set up at the Johnson Youth Center. Diamond Park Aquatic Center. So here's a picture of Thunder Mountain School in the background, of course, with the loop field in the front. And this is under the parking lot now that's out in front of the pool. There's a few pictures. It's the same outfit, Gregory Drilling. They did both the airport and the pool. And these are just some of the pictures as they're getting going. Here's the pretty much all the mains you see crisscrossing the whole pool, picking up the pool loop field, picking up all the wells that went through there that are going down about 350 feet. We have 164 wells, 1-inch diameter pipe. I believe it ended up being somewhere in the like 24, 25 miles of pipe. And then, of course, the horizontal piping is manifolds it all together. As you can kind of see right in here, we're bringing a manifold, and these are the mains that bring it all the way back into the pool. I don't know if I got a shot of the pool. I really don't. So we came into the pool, and then just inside the pool is this manifold where those 4 sets of mains are now brought together into one pipe, and then they're brought over to this thing right here, this big box, which is a very large heat pump, water-to-water heat pump, 120-ton heat pump. A ton is 12,000 BTUs per hour, for those who don't know that. And that heat pump there supplies heated water for the pool heating and the radiant floor heating of all the locker rooms. And it also supplies air heating to all the ventilation. So the only thing that doesn't supply heating for is the domestic hot water. One of the reasons for that is there's a limitation on what a heat pump can raise its load temperature to, and that's about 115, 120 degrees max. So it's difficult to get domestic hot water out of it. They do it quite frequently down south, but for a little bit different reasons. So generally this is suited for heating and not necessarily domestic hot water because of that temperature limitation. And then this middle picture here, we have actually 6 water to air heat pumps in the pool that supply like the like the meeting room and the main entry and those kind of areas. And these actually will do cooling, so they're heating and cooling of some of those areas. So these are very similar to the water to air heat pumps at the airport, but they're just a vertical type. So these actually look just like the ones pretty much that are at AEL&P. For those of you that haven't been in the pool, that's the pool. That's the pool at night before anybody was in it. So current and upcoming geothermal projects. Right next door, actually right across the road over here, is the new SHREF facility. That's the snow removal equipment facility. It's going to be a building. The airport's really excited about this, where they're going to be able to park their loaders and their outdoor equipment. Right now they pretty much park them outside, shortening the life of them. So the new snow removal equipment facility is going to move all of the maintenance offices and shops over to this facility, as well as storage for most of their equipment. And that building is going to go essentially right next to the wings hangar over here. And that project is still in design. But the project manager came to us and said, gee, is there an opportunity for a loop field? And I was looking at her and going, well, like what kind, you know? And she said, well, we have this big pit over here next to which was at the time filled with beautiful lupin. So, and they needed to put the sludge from the floatplane pond somewhere. In fact, it was going to be kind of a nightmare because they didn't have much of a place to put it. And so the idea then was put forth as, well, what if we lay out a horizontal loop field, tubing, you know, in a horizontal fashion, and then you pour all the sludge on top of that? Will that work? And I'm like, well, let's look at it, you know. And sure enough, it was pretty much a no-brainer once I started getting into it. And I think I have some slides on that facility because it was just recently completed. But essentially, we got 4.6 acres of 3/4-inch tubing, 1 foot on center, 2 layers of it, and it's essentially like a huge radiator. So we're sucking up the heat from the ground, and I did a quick calculation. There's 184 miles of tubing, and it's all manifolded together, and it's brought back, and it's going to be brought back to the new snow removal equipment facility, and where we'll use it then in a similar fashion as the pool, squeeze the heat out of that, and then use it for the heating of appliances in the new Schreff facility. Auk Bay Schools, I'm sure most of you have heard, is considering a geothermal system. There's going to be a vote in October on that for additional funds to go to that. Preliminary projection was 60 boreholes there to supply all the heating needs for the school. Johnson Youth Center, they are doing a renovation of that facility, which is right below the hospital, and they decided to go geothermal on that. We've got 24 wells there that go down 400 feet, and that will supply pretty much most of the heating for the main building of the Johnson Youth Center. That project is actually under construction. The site work is part of the geothermal is part of the site work, and that's been already let out. So I expect in September that they'll start the boreholes on that. Johnson Youth Center, we had 2 test wells that I applied that test apparatus to and tested for the thermal conductivity. U.S. Forest Service lab, which is going to go next to the Egan Library at the campus here in Southeast, the Juneau campus, and that's going to also be 24 wells. They've made the decision to do that after an extensive analysis of heating options. And that's 24 wells at 350 feet each. And I expect in September they're going to start that one too. Other projects. I know that the State Libraries and Archives and Museum is considering some form of geothermal. I think they're just getting started on that. I think the initial look is going to be at a seawater type system. But if that doesn't pan out, then they might look at geothermal. In terms of residential, which I really don't get involved with too much, except just advising for a number of reasons, there's at least 14 or 15 geothermal systems that I'm aware of in Juneau. Some of them use slinkies down in the tideland, others use straight run or slinkies up on their property that they were able to excavate. There's 1 or 2 that are vertical boreholes, but they appear to be a pretty exciting alternate to heating. This is back to the snow removal equipment, just kind of showing you that there. This is the horizontal loop field, and I didn't get a real good picture of the entire 4.6 acres. This one kind of shows it, but it's difficult to see the tubing. But here you can see this main trench is gathering all of the 3/4-inch tubing from both sides, and so this is the tubing that then goes out. It goes out about 170 feet, wraps around a few times, come back. Each tube's 1,000 feet long, and then connects up to the mains that run down this center trench. back to the Johnson Youth Center, I just wanted to show you these guys, a different driller, and then a rendering of the Forest Service lab, which has nothing to do with geothermal. An Ock Bay school. Lessons learned. The initial cost, as I'm sure you're all aware of, is expensive. I mean, you know, I think the ballot issue is asking for $1.4 million of additional funds for the Ock Bay school. Well, look, you know, you compare that to a above-ground fuel tank. It's a no-brainer, you know. Yeah, but the way you need to look at these systems, particularly I think if these are public funds, in my opinion, is the life cycle cost of it. And for the Ock Bay school, I believe they looked at a 40-year life. And they compared biomass systems, you know, wood pellet type systems. They compared oil, they compared electric, and they compared geothermal, and they compared air source heat pumps. And the ground source geothermal paid out in a 40-year life. So you really need to look at the big picture in terms of that. You know, if you're a private business owner and you're building a brand new building and you're planning on selling it in 5 years, are you going to want to invest heavily in something at the beginning? Probably not. That's just kind of the way that's going to go. So you got to look at the big picture at this. Determining thermal conductivity, like I said, from the test wells, that's really important. I gave you the range. It was essentially double at Ock Bay School what it was here at the airport. Well, that means a lot. And heat pump technology literacy. This is a really big topic. And essentially what it means is the maintenance people, the service people of the community need to, in order to make this successful, our literacy really needs to jump up. And, you know, we're on a steep part of the learning curve. Yes, there's one or two service, you know, contractors in town that have been doing this a while, but they're not enough. And so problems, you know, ensue, you know, if you got, you know, one of your heat pumps goes down and you need someone right away. Maintenance folks are still on, you know, on the steep part of the learning curve of, you know, operating, you know, heat pumps. You know, they're a pretty sophisticated piece of technology. I would highly encourage the city and borough, if they're going to keep up with this, is they should really have one or two people in the maintenance department that is savvy in heat pump technology. It's going to pay off. So that is a problem, but I think it's just going to get better as time goes on. And another one is contractor expertise. When we started out on the pool and the airport, we knew we essentially had to hire either an Anchorage or a Seattle or Washington-based contractor. There was one fella here locally, but he just wasn't up to speed, you know, with the amount of drilling that was going to go on. And so that's why we ended up with a Washington State contractor when we did the airport. Since then, there is a contractor that has moved to Southeast. He actually lives in Juneau. And he did the test wells at the Johnson Youth Center and the Ock Bay site. And so I'm really glad that at least there's one fella here locally that has a lot of experience with geothermal. And he's essentially told me he's going to leave his rig here in Southeast, and that's not taking it out, so which is good news. So which should hopefully help keep the, you know, the bid costs down on, you know, future projects too. Just give you a little shot there of different types. Let's see, I had two more things here. Oh yeah, I wanted to make sure told you that the heat pump technology essentially moves heat. I know I said that at the beginning. Doesn't make up the heat. And it essentially uses a Carnot cycle, a refrigeration cycle, to take heat from one entity, and I like to say compress it, you know, to a smaller package then, and then send it out to you know, the heating needs. And that cycle is called the Carnot cycle. It's a really efficient refrigeration cycle. Any questions? Yeah.
Even though these are really efficient compared with resistance electric heat, it does each additional load on the hydro generation power we have here. And I'm wondering what you think the potential is in this city for lots of projects. We're going to run out of hydropower before too long, I guess. And I'm assuming that none of these projects are replacing resistance electric heat, so we're not saving. We're actually adding increments to our overall load. Do you have a sense of how far we can go with this before we run out of capacity? And I mean, this may be something Tim can
Right. No, I don't have a sense. Tim could probably answer this better. You do need to keep in mind that the efficiency of the heat pump system is anywhere between 250 to 400% efficient. So, if you paid $10 for your electric heat boiler, you'd be paying say $4 for the electric heat or the heat that you get out of the heat pump. So, yes, you would add electrical load to the entire system, but certainly not as much as you would with an electric boiler.
Bart, we really support these heat pump systems at AEL&P because of the tremendous efficiency that we get out of them. And our concern is that the price of oil will drive people to resistive electric heat, in which we would have to more than double our hydro capacity to take that much heat on. With these geothermals, with these heat pump systems, it may be manageable. We'd have to develop some more hydro, but not to the extent that we would with resistive heat. So we
foresee AEL&P being able to handle pretty wholesale conversion to geothermal heat pumps in a lot of residences?
It's so expensive that I don't think that we'll see at least a rapid growth in it, just because of the cost of it.
Thanks.
Yeah.
What's the difference between this heat pump and Bernie Carl's system? You're taking 42-degree water and raising it to 120, and he's taking 160-degree water and raising it to 900.
Right. It's essentially hot and cold geothermal. Yeah. So we are essentially taking ground that was warmed by the sun and then using that heat. Okay. So it's solar-powered heat that we're getting out, whereas Bernie Carl is taking, heat from, deeper down. So it's Earth's core heat.
Can you ratchet yours up using his system to take 42-degree water to?
Nope. No, it's an inefficiency of the heat pump itself. 120 is about the max you're going to get out of the system. Yeah.
I was thinking about high-density areas just in terms of kind of aggregation of buildings. Is there any limitations in building structures on top of existing tube fields?
It's probably the nervousness of the engineer. It's done. We actually considered it briefly for the new Alaska Heritage Institution, the Sobolov Center downtown, but I think everybody was pretty nervous about burying a well underneath a building. Yeah. But it's done on some campuses and stuff down south. Yeah. Murray.
As I understand it, and that picture is helpful, you drill a hole for the fluid to go down, and there's another one for it to come up.
That's in the two pipes are in the same hole, though.
Down at the bottom, you got to connect one hole to the other hole. Do you send a little guy down there to drill sideways, or?
It's just one hole. Actually.
Oh, really?
Okay. Yeah, one hole with two pipes, and you have a U-tube at the bottom. So the two tubes are right next to each other.
And they're insulated so that they don't bleed heat back over?
No. The flow rate is slow enough that whatever you're losing, when you first start out, it's pretty much equaling out as you get out of the hole. So the fluid's moving pretty slow, still turbulent, but it's moving slow enough where that interaction isn't there. Now, what I have done, to be honest with you, the guys down south think I'm a little crazy for this, but I'm still convinced it works. Is I insulate this pipe. Is I make them insulate the horizontal stuff. Because the temperature coming out is, at design anyway, is like 31, 32 degrees, so we've got to use an antifreeze. And then coming back, it's at design, it's coming back at about 38 degrees. So at design, we're looking at a 6 to 7 degree split. And so I would just as soon limit that, in the big mains, where we have a lot of the water. But down in the hole itself, it doesn't seem to really matter in that sense. I didn't really answer your question very well, I don't think, Murray, but...
There's no little guy involved.
Yes.
On your thing up there, for your drilling, you said 350 feet at the airport. That was to get down into the rock? work?
No, they never hit bedrock.
Okay, so then,
So we're just
Wouldn't it be
gravelly
cheaper
moraine
just-
is what they call it.
wouldn't it have been cheaper just to put the pond type or the field type in rather than drilling all in 300-foot holes?
Well, where's the pond? So, I mean, yeah, we considered it at the police station, when we originally did the police station, but there's some politics involved. They didn't own the pond and such, so we pretty much abandoned that. But that was the first spot that we looked at where you could put out slinkies and just bury them down in the water. Yeah, that obviously is a much easier spot. Now, the closest pond at the airport, because we did talk about this, was the floatplane pond. But now we had to get all that tubing back to the airport, and that was expensive, just getting it all back there. So, if you have a ready source like a pond or the sea, perhaps that is a cheaper method. But I hasten to say that that's the panacea, because you got problems with the sea. You go out there and you put some tubes down in the bottom, and you weight it down. Well, now growth's going to go on that. And anything, that kind of stuff that starts to grow on the pipes then lowers the thermal conductivity. And so now you got to go down there and clean it, that kind of stuff. And that's why we like being in the ground, because pretty much nothing's going to happen to it. I mean, it's, these tubes at the airport, I envision should be there 50, 75 years from now. So, yes?
Can residue build up inside the pipes? I mean, what kind of...
Yes.
Like for residential application.
Yeah, it's a closed system, but you're right. You can get a little bit of a sludge, accumulating that, just like you can with a hydronic, heating system. And there's ways to clean that out. You can put some stuff in there, clean it out, and circulate and such. And that's where the service guys come into play, of course. Yeah.
Can you explain the exchange technology a little more? In other words, okay, you got 7-degree difference, so it brings into the building. Explain the science of the exchange technology.
Okay, sure. We actually, all of us have a heat pump in our house. It's a refrigerator, right? So you put something warm inside the refrigerator, and then through the heat pump of the refrigerator, it has tubing in the walls of the refrigerator. Heat is absorbed by that fluid that's in the tubing, which is a refrigerant, and usually it's R12. In the old systems now it's R22 or R410A. And then through the Carnot cycle, and I got to look at my little cheat sheet here. You essentially warm that up. It wraps around to a compressor that compresses, essentially I like to say compresses the heat down into a smaller package, and then sends that around to whatever's going to reject the heat, which is in the case of a refrigerator, is the coils in the back. So when you put your hand in the back, it's usually warm. It's like 80, 90 degrees out of that, right? So that's the heat that's coming out that was inside the refrigerator. And that runs around. You run through an expansion device, which helps turn the refrigerant into a liquid. And then that runs back around to your heat exchanger, which is the inside the refrigerator that then picks up the heat again. So it's a continuous cycle like that. It's called the Carnot cycle. It's one of the most efficient refrigeration cycles out there. That's kind of it in a nutshell. I can go over more. Yeah.
Well, thank you.
Sure.